Empirical relations for force convection heat transfer. Okay, so when you're designing crucial equipment like heat exchangers, you're going to run into really complex flow problems inside the pipes. I mean, trying to solve for turbulent flow from scratch, it's just way too tedious. That's why we rely on powerful, tested shortcut formulas, known as empirical correlations. First, you have to know that these correlations are all built using key dimensionless numbers that basically capture the physics. There are three main ones: the Nusselt number, which tells you about the heat transfer, the Reynolds number, which tells you if the flow is smooth or chaotic, and the Prandtl number, which kind of relates how fast heat and momentum are moving. Second, for a fully developed turbulent flow in a smooth tube, the go-to formula is the classic Dittus-Boelter equation. A key thing to remember here is that one of its exponents, n, actually changes. It's 0.4 when you're heating the fluid, but it's 0.3 when you're cooling it. Finally, for laminar flow, we switch over to different relations designed for that calmer regime. In these equations, you'll often see the Peclet number pop up, which is pretty simple. It's just the Reynolds number times the Prandtl number, and it's essential for modeling that smoother flow. So, these foundational empirical correlations provide crucial, practical tools for solving real-world heat transfer problems. Let's dive into more detail.
If you're in chemical engineering, you've probably spent tons of time with those clean, perfect theoretical equations. But what happens when things get messy out in the real world? Well, today, we're going to decode one of the most powerful tools in an engineer's toolkit for dealing with exactly that mess: a famous formula for heat transfer. Okay, so picture this. You're designing a real heat exchanger. The fluid whipping through those pipes isn't moving in some perfect, predictable way. Nope, it's turbulent. It's chaotic, and its properties are changing as it heats up. Trying to solve that with pure physics from the ground up, the textbook itself calls it very tedious, and that's putting it mildly. It's practically impossible. So when pure theory hits a brick wall, engineers get practical. We use something called an empirical correlation. See, this isn't some equation that a genius came up with just by thinking really hard. Instead, it's built by running tons of experiments, collecting a mountain of data, and then finding the formula that actually fits what's happening. It's the bridge from the clean world of the lab to the messy reality of a chemical plant. All right, here's our game plan for today. First, we're going to dig into why we even need these tools in the first place. Then, we'll dissect the famous formula itself, meet the key numbers that make it all work, watch it in action with an example, and finally, talk about how you choose the right tool for the job. Okay, so why can't we just use a simple little equation for heat transfer in a pipe? I mean, it's just a pipe, right? How hard can it be? Well, in most industrial settings, the flow is turbulent. That means chaotic eddies, swirls, the fluid is mixing like crazy. On top of that, as the fluid heats up or cools down, its properties, like its viscosity, are changing. All of these things at once make a purely theoretical solution just way too complicated. So to tackle these messy problems, we turn to these things called correlations. And honestly, one of the most famous ones in all of heat transfer is the Dittus-Boelter equation. It's an absolute classic for figuring out heat transfer when you've got turbulent flow inside a nice, smooth tube. And boom, there it is. I know, at first glance it looks a little intimidating with all those letters and exponents, but trust me on this, the beauty of this equation is that every single part of it tells a piece of a story about what's physically happening. We're going to take it apart, piece by piece. The real magic here, the elegance of this whole approach, is in these three special dimensionless numbers. What they do is brilliant. They take a whole bunch of physical properties, like velocity, density, viscosity, you name it, and they bundle them together into these neat little packages that describe the physics of the situation, no matter what fluid you're using or how big your pipe is. First up, we've got the Reynolds number, or RE. The best way to think about it is as a tug of war, a battle between two forces inside the fluid. On one side, you have inertial forces. They want to keep the fluid moving and stir up chaos. On the other side, you have viscous forces, which are like fluid friction, trying to keep everything smooth and orderly. The Reynolds number tells us who's winning that fight. And this right here, this just nails the difference. When the Reynolds number is low, viscosity is winning that tug of war. You get that smooth, predictable laminar flow. Think of a lazy, slow-moving river. But when the Reynolds number is high, inertia takes over and you get chaotic, well-mixed turbulent flow. We're talking whitewater rapids. And the Dittus-Boelter equation, it's made for the rapids. Okay, next up is the Prandtl number, PR. This one, it's all about the personality of the fluid itself. It's basically asking, Which moves faster through this fluid, momentum or heat? For something like a liquid metal, heat zips through way faster. For gases and water, they're a little more evenly matched. It's a core property of the material. And finally, we get to the Nusselt number, nu. This is the answer. This is the whole reason we're doing the calculation. It tells us how much better the heat transfer is because the fluid is moving, that's convection, versus how it would be if the fluid were just sitting still, that's conduction. So a big Nusselt number, that's great news. It means convection is winning and we're getting fantastic heat transfer. So you might be wondering, where did they get those weird numbers, like 0.023 and 0.8? Did they just pull them out of thin air? No way. They come from data. Researchers ran countless experiments, plotted their results on a special log-log graph, and saw that the data formed a pretty straight line. The slope of that line becomes the exponent, and where it crosses the axis gives you the constant. It's a beautiful example of how engineers take a mountain of real-world data and find the simple, powerful pattern hidden inside.
Okay, so we've met all the key players. Now let's see how they actually team up in a real calculation. We're going to walk through an example inspired right from the textbook to see how this equation actually gets put to work. All right, let's get practical. Imagine you've got hot air at 200 degrees Celsius zipping through a 1-inch tube. The wall of the tube is a little hotter. Your job is to figure out how much heat is actually getting transferred. First things first, we need to look up the properties of air at that temperature so we can calculate our special numbers. So after we plug in all our numbers, the density, velocity, diameter, and viscosity, we get a Reynolds number of 14,756. Now, the rule of thumb is that anything over about 4,000 is turbulent. So at nearly 15,000, we are definitely in turbulent territory. That tells us, yep, Dittes-Boelter is a good tool for this job. Next up, the Prandtl number. For our air, it comes out to about 0.681. Remember, this is just a fundamental property of the air itself at this temperature. It's part of its heat transfer personality. Okay, this is the moment of truth. We just take those two numbers we found, Reynolds and Prandtl, and plug them right into the Dittes-Boelter equation. The Reynolds number gets raised to the power of 0.8, the Prandtl number gets raised to 0.4, we multiply it all by that magic constant 0.023, and bam, we get our Nusselt number, 42.67. So, what good is that? I mean, it's just a number, right? Well, this is the key. Because we know how the Nusselt number is defined, we can easily rearrange the formula to solve for h, the convection heat transfer coefficient. And that little h, that is the absolute golden ticket. It's the number you need for pretty much every practical heat exchanger design out there. So Dittes-Boelter is amazing. It's a workhorse. But a huge part of being a good engineer is knowing the limits of your tools and knowing when to reach for something a little more specialized, because it's definitely not the only correlation in the toolbox.
And this is super interesting. Here are a couple of other options, also from our source material. Let's say you have huge temperature differences. The Cedar-Tate correlation is your friend. It adds a little correction factor for how the fluid's viscosity changes. Or what if you need crazy high accuracy? Then you might use the Pituhoff equation. It's more of a beast to calculate, but it's also more precise. You know, this quote from the textbook just perfectly sums up the whole point. For design and engineering purposes, empirical correlations are usually of greatest practical utility. While the deep theory is critical for understanding why things work, when it's time to actually design and build something, these practical, data-driven formulas are what get the job done.
All right, let's wrap this up. What are the big things to take away from all this? First, empirical correlations like Dittes-Boelter are how we solve messy, real-world problems that theory can't handle alone. Second, those dimensionless numbers, re, p, and nu, they aren't just letters. They tell a physical story about what's going on. Third, the Dittes-Boelter equation is your go-to powerful tool for turbulent flow. And finally, and this is so important, great engineering is all about choosing the right tool for the specific job you're facing. And that brings us to one final, really important thought to leave you with. These correlations are powerful because they're built on real experimental data. But what do you think the risks are when you try to use one of these equations way outside the range of the data it was built from? It's a critical question about understanding the limits of our tools, and it's where you really start to think like an engineer.